Topic in the video belongs to the lesson Moving Charges and Magnetism. Learning outcomes of this video are force on a current carrying conductor in a uniform magnetic field, Fleming's left hand rule, and force between two parallel current carrying conductors.
Namaste students, this is Chalpati, faculty in physics. Now I am going to explain about force on a current carrying conductor in uniform magnetic field, Fleming's left hand rule, and what is the force between two parallel current carrying conductors. Before going to the topic, I want to give some clarity about Fleming's left hand rule. For suppose, consider it is a current carrying conductor. This is in uniform magnetic field. For suppose that uniform magnetic field is perpendicular to the display. For suppose, according to your observation to your display, the magnetic field for suppose inward. Then what is the force on this current carrying conductor? For example, consider Fleming's left hand rule wise, you have to keep your three fingers like this. Three should be perpendicular to each other. Perpendicular, perpendicular, and this perpendicular. Okay. So for example, the thumb indicates the force direction. If the current passing in the direction with respect to the middle finger and this forefinger indicating the magnetic field. For example, conductor, current passing in this direction and magnetic field is perpendicularly inward, then just observe the force direction will be upward. So if suddenly current passing in the conductor which is placed in uniform magnetic field, suddenly it experiences a force upward. So that we are going to learn what are the factors affecting on it in the topic.
Force on a current carrying conductor in a uniform magnetic field. To get the expression for force on a current carrying conductor and to analyze the factors affecting the force on this current carrying conductor, consider a current carrying conductor as shown in the figure. For suppose L is the length of the conductor in uniform magnetic field. For suppose the magnetic field acting in a direction which is making an angle theta with the length and A cross sectional area. For suppose I is the current passing along positive x-axis. For suppose here current passing in one direction means according to conventional current this is the direction, means indirectly electrons are moving in opposite direction. Electron direction and current direction completely opposite. So here electrons are moving along the negative axis, that means current passing along positive axis. This is our consideration. So according to this assumption, for suppose electrons are moving in negative axis, consider the velocity is Vd. Here Vd means drift velocity. For suppose the number of electrons in the conductor are, for suppose small n nothing but number of electrons per unit volume, that is electron density of the conductor. Now, so due to this current and the conductor is in magnetic field, what is the force? To get the force expression, if you analyze, these are the electrons are moving in magnetic field. So if you can get the expression for the force on these electrons, that means indirectly the force on the entire conductor. If you can get the total force on all the electrons, that means indirectly it is a force on the entire conductor. So that is why according to our known formula, force on a particular charged body, we can write the force on a charge q in a magnetic field B moving with a velocity v is F equals to q into v bar cross b bar, the general formula. So if you can mention like this, that means v bar cross b bar nothing but vb sin theta, but it is a vector, but we are taking only magnitude. Force is having particular direction. Presently I will explain magnitude and finally we will discuss the direction also, but because force is a vector, direction also we should analyze. For example, q charged body will experience a force like this. For suppose if you consider only one electron, what is the force on this electron due to the magnetic field B? So for that purpose, instead of Q, if you substitute E, then you will get force on the electron. So that we can mention like this: the force on the electron moving with velocity Vd in magnetic field B is, for suppose consider F dash is the force, then charge E, velocity Vd, magnetic field as usual, and theta we consider, so sin theta. So this is the force on one electron, but there are many electrons. For suppose there are capital N number of electrons inside the conductor according to the finite size, that we can analyze with respect to small n. That small n we can also write like this: in the conductor, electron density n equals to number of electrons per volume. So from this we can mention number of electrons equals to small n into volume. So here volume nothing but volume of the conductor. So that volume we can mention as the product of cross-sectional area into length. So the number of electrons in the length L of conductor is capital N equals to small n into volume. So number of electrons equals to small n into volume. So small n into volume nothing but cross-sectional area into length. Further, the total force F on the free electrons in the conductor of length L is. So here we got n number of electrons, and as well as we know the force on one electron. So in the previous slide we already got F dash, that is force on one electron. Now there are n number of electrons, so force on one electron is F dash, force on two electrons is 2F dash, force on n electrons is NF dash. So that we can apply. So the total force on the entire conductor F equals to F dash into n. Now F dash value we can substitute, and as well as n value also we can substitute. F value if you mention, therefore F equals to F dash E Vd B sin theta, and capital N nothing but n into Al. This one you can reshuffle and we can mention like this: small n into E into capital A into Vd, and remaining B L sin theta. So why I mentioned like this? Reason, so inside the bracket the total expression is having some meaning. In current electricity lesson, for example, in a current carrying conductor, for example, Vd is the velocity of the electrons and n is electron density and A is the cross-sectional area of the current carrying conductor, then the current passing through the conductor is nothing but NEA Vd. So that formula if you apply, so instead of this one we can mention directly current I. That is, we know that current flowing through the conductor is I equals to NEA Vd. So instead of NEA Vd, if you substitute I, then the expression will be F equals to ILB sin theta. So here L is the length element and B is the magnetic field. Both are vector quantities. We can analyze as vector quantities. So we can write as a vector also. That implies F bar, or simply capital F with bold letter. It indicates the vector equals to I into L bar cross B bar. Now different cases. So this is the expression for the force on the current carrying conductor. Still the direction is pending. So first I will discuss the cases and afterwards I will give you the direction also. First case, if theta equals to 0 or 180 degrees, that means the angle between length element and magnetic field direction. So it's either parallel to each other or anti-parallel to each other. So what it may be, the total value will be 0. If the current carrying conductor is parallel to the magnetic field or anti-parallel to the magnetic field, then the force will be 0. Why? Because the sine 0 or sine 180 degrees equals to 0. So if it is 0, then net force will be 0. That means we can write, hence a current carrying conductor placed parallel to the direction of magnetic field experiences no force due to the magnetic field. Case 2, if theta equals to 90 degrees. In case 1 we already discussed theta 0 180 degrees. Now a special case, that is theta equals to 90 degrees. Then the force is maximum. Reason? We know force F equals to Bill sin theta. So in that theta 90 degrees, so 90 degrees value 1, so that is why the maximum force will be Bill, B-I-L. For that there is a condition, that is the current carrying conductor placed perpendicular to the direction of magnetic field, then only the force is maximum. So it experiences maximum force due to the magnetic field when the current carrying conductor placed perpendicular to the direction of magnetic field. Next, Fleming's left hand rule. So this Fleming left hand rule will give the direction of magnetic field. So here the current carrying conductor is getting the force if you place in uniform magnetic field. So according to the direction of magnetic field and according to the current direction, it is getting the force. If you change the direction of current, means if you change the length element with respect to magnetic field, there is a change in force. So with respect to that, Fleming used his left hand and he placed the left hand fingers like this. Means according to the diagram, we have to stretch the left hand fingers 3, each one perpendicular to another. Then, so here if you observe, the middle finger, for example, it is indicating the current direction, and with respect to the current direction, for example, magnetic field is perpendicular to that one, for suppose that is magnetic field B, then the force definitely in the direction of thumb. If you can arrange the 3 fingers of your left hand according to the diagram, then the force direction will be the thumb direction. So for that, one example, just consider the diagram. So according to the diagram, so here there is a current carrying conductor. I is the current passing in the conductor. So this is the direction of current. Now for example, L is the length element, but here there is no much function to analyze the force on the current carrying conductor, but the B, magnetic field direction, is perpendicularly inward. So here into symbol indicates the magnetic field is perpendicularly inward. If the magnetic field is perpendicularly outward, then we have to indicate dot and circle. So on the paper or anywhere, for example, magnetic field indication with dot and circle means that is perpendicularly outward. So here only into, that is perpendicularly inward. So magnetic field inward and current passing towards left. Now keep your left hand 3 fingers. The middle finger try to arrange in the direction of current and keep your 4 finger in the direction of magnetic field, that nothing but in the inward to the display. Then you can check your thumb will indicate the direction like this. So this is the force direction, means the current carrying conductor experiences a force upward if current passing in this direction. Now if you change the current direction or if you change the magnetic field direction, definitely the force direction will change. Next, force between 2 parallel current carrying conductors. For that, consider 2 current carrying conductors. If you place the 2 current carrying conductors very near to each other and if you pass the current in the same direction, what will happen? If you change the current direction in one of the conductor, what will happen? Whether they will attract each other or repel each other or nothing will happen. So let us see. So with this topic you will come to know the force between the 2 parallel current carrying conductors. There is a force either attractive or repulsive that we should analyze. For that, consider 2 parallel current carrying conductors. For suppose A1 B1, one current carrying conductor, A2 B2, another current carrying conductor. For suppose in first conductor I1 is the current, in the second conductor for example I2 is the current. Now due to this I1 current, it is a current carrying conductor. According to Biot-Savart's law, every current carrying conductor, it is a straight current carrying conductor and both the current carrying conductors at a distance r. So definitely around this current carrying conductor there will be a magnetic field. So we can get the direction of magnetic field by using Ampere's law, and the magnitude of magnetic field we can get by using Biot-Savart's law. So first, according to Ampere's law, current passing upward, then the curling of fingers indicates the magnetic field direction. So here at P or on the wire, everywhere the magnetic field will be inward. So that inward indication, that is into and circle. So here B1 is the magnetic induction due to first wire on the second wire. Magnetic field applying on the second wire due to first wire. So that is why here B1. Here B1 is the magnetic induction due to first wire. Similarly, I2 is the current carrying conductor, means I2 is the current passing in the second current carrying conductor. So due to this, for example, magnetic field B2, that also you can get by using Ampere's law. So according to the Ampere's law, thumb indicates the current direction. Then the curling of fingers you can see here, those will come outward. So that is why here dot and circle means on this first current carrying conductor, due to the current in the second current carrying conductor, the magnetic field will generate upward, means outward to the display. So due to these two magnetic fields, there will be a force. So here direction we will analyze. First let me explain the magnitude, afterwards I will give the clarity about force also. So to get the magnitude details, we should use Biot-Savart's law. So magnetic induction at a point P on the conductor A to B2 due to current I1 passing through A1 B1. So this current carrying conductor producing magnetic field B1 at this point, which is at a distance r, that we can write, it is considered as infinite current carrying conductor. Then B equals to mu naught I by 2 pi r. So here according to the symbols, I1 is the current and B1 is the magnetic field we consider. So due to I1 current passing through the first wire, B1 magnetic induction coming at point P on the second current carrying conductor. So now I2 current carrying conductor in the magnetic field. So just now we analyzed a current carrying conductor in the magnetic field. Definitely there is a force. That force expression we can analyze now. So for that, the force on length L, for suppose consider L length element in A to B2. So definitely there is a force. That force here, the magnetic field is acting perpendicularly inward. So according to Ampere's law, here the magnetic field perpendicularly inward. So due to inward magnetic field, means the current carrying conductor is perpendicular to the magnetic field. So definitely the force will be bill. So that bill we can write like this. So F2 is the force on second carrying conductor. So why I mentioned 2, the force on the second wire, that is equals to due to magnetic field B1 and current I2 and length element L. Okay. So again I am repeating the explanation. Here the second wire is in the magnetic field of first wire. So the force on the second wire due to current I2. So due to current I2, force will be bill. So B nothing but magnetic induction due to first wire. So that is why B1 I2 L. Now if you substitute B1 value in this expression, then you will get F2 equals to mu naught I1 I2 by 2 pi r into L. Further, L you can shift towards left side, then you will get force per unit length. F2 by L, nothing but force per unit length, which is equals to mu naught I1 I2 by 2 pi r. So this is the final expression, but we analyzed only for second wire. Similarly, the same thing if you study for first wire. For example, this first current carrying wire I1 is in the magnetic field of second wire. So second wire producing magnetic field B2, but that is outward. So what it may be? So outward means according to this current carrying conductor, magnetic field is perpendicular. So B2 magnetic field is perpendicular to the current carrying element. So the force is bill. So again that bill we can write. So B2 I1 I2. So B2 value, if you substitute, B2 nothing but mu naught I2 by 2 pi r. So if you analyze, you will get the same expression. So directly we can derive F1 by L equals to mu naught I1 I2 by 2 pi r. So which is equals to F2L. So both are identical conductors, and for example, according to the currents I1 and I2, so you will get the same type of expression. Next, commonly we can write now the force between two current carrying parallel conductors per unit length. So here F is nothing but force per unit length. Either you can write F by L or F. So if you mention F means wording, we have to write current per unit length equals to mu naught I1 I2 by 2 pi r. So here with respect to first wire F1 by L, with respect to second wire F2 by L, but in general F by L. So F by L nothing but force per unit length. So here F indicates the force per unit length. So which is equals to mu naught I1 I2 by 2 pi r. Now the force direction. To get the force direction, consider the diagram. So now first diagram. So here current in the first wire, for example I1, in second wire also current passing in the same direction. So in both the wires current passing in the same direction for suppose. Then due to first wire you can analyze according to Ampere's law magnetic field around the current carrying conductor, and similarly here also on the second wire also according to Ampere's law the magnetic induction will be like this as shown in the diagram. According to Ampere's law, curling of fingers only the magnetic field direction. So here you can see lines of force are coming like this, here outward to the display and here inward to the display. So here inward, here outward. So try to remember. Now we can apply the Fleming's left hand rule and we can get the exact force direction. So for that, first consider the Fleming's left hand rule. So according to Fleming's left hand rule, forefinger indicates the magnetic field direction, middle finger indicates the current direction, then thumb indicates the force direction. So for that you should apply your own thought now. Consider first wire here. So here current direction will be indicated by middle finger of your left hand. So keep your left hand middle finger in the direction of current, and the magnetic field at that first current carrying conductor, you can see here the magnetic field is outward. So your forefinger of your left hand should be outward to the display and the current direction should be upward. Okay, so keep your left hand little bit above your head, then only easily you can indicate. So the display, consider the display. To the display your forefinger should be outward and the middle finger should be upward. So middle finger of left hand upward current direction and magnetic field is outward to the display. So if you keep, then the force direction you will get, the thumb you will get in this direction. So that is towards the second wire. Same thing analyze for the second wire also. So magnetic field here inward. So according to the Ampere's law, the curling of fingers coming like this. So according to the curling of finger, here magnetic field inward. So it is easy to indicate. Indicate first forefinger of your left hand inward to the display. Outward to the display is little bit difficult, but inward to the display is easy. So keep your forefinger of left hand towards the display, and means inward to the display, and keep your left hand middle finger in the direction of current I2. Then definitely you will get your left hand thumb direction in the direction of F2. So means if two currents are parallel to each other, then the force on the conductors coming both are in opposite direction and as well as towards the conductors. Both are opposite but towards the conductor, means both will attract each other. But same thing if you analyze for anti-parallel conductors. Anti-parallel means current passing in one conductor in one direction, in another wire is in opposite direction. If current passing in opposite direction, what will happen? So here it is a clear indication is there F1 F2. Let us see whether we are getting in the same manner or not. So again here according to the current direction, so Ampere's law if you apply for the second wire, so current direction I2 like this. So due to that here curling of fingers will generate like this. That means here magnetic field inward, and as well as here also magnetic field inward. Okay, so here current direction is opposite, so downward. So thumb you have to indicate towards down, then curling of fingers will go inward. So that is why magnetic field inward. So keep your left hand forefinger inward to the display and keep your left hand middle finger in the direction of current I1. Then the thumb indicates like this. Same thing here, magnetic field on the second current carrying conductor, that is also inward. So keep your forefinger inward to the display and show your middle finger in the direction of I2 current. Then the thumb direction will come towards right side. That means again forces are in opposite direction and both are away from each other. That means if current passing in the parallel conductors is opposite, then both will repel each other. So that we can conclude simply like this. Hence two linear parallel conductors carrying currents in the same direction attract each other, while carrying currents in opposite direction they repel each other. One problem, example problem. Say current of 20 ampere flows through each of the parallel long wires which are 4 centimeters apart. Compute the force exerted per unit length of each wire. So first solution given. So if you read the question, you can write the given data. First current is same in both the wires, so I1 I2 both are same, so that is 20 ampere. Distance between the wires that they mentioned as 4 centimeter, that is a CGS unit. Be careful. So here A is ampere MK system and centimeter means CGS system, so compulsory we have to convert into MK system. Here centi means 10 to the power of minus 2, so then it will be 4 into 10 to the power minus 2 meter. So this one if you analyze as a diagram, they said current passing through each parallel wires, so both are parallel, and as well as distance between them is 4 centimeter, current is 20 ampere. Then they are asking force per unit length, that is F by L. So we know the formula, just now we derived, that is mu naught by 2 pi into I1 I2 by R. So here mu naught value 4 pi into 10 to the power of minus 7. If you substitute current value and R value, you will get mu naught value 4 pi into 10 to the power minus 7. I1 I2 both are same, 20 into 20 by 2 pi into R value 4 into 10 to the power of minus 2. So further easily you can simplify this one. 2 pi get cancelled, 4 pi by 2 times, and the 2 divides 4 by 2 times, and the 2 divides the 20 by 10 times. So then finally here 10 to the power of minus 2 get cancelled, so only minus 5. So then you will get 200 into 10 to the power of minus 5, or we can also mention like this, 2 into 10 to the power of minus 3, that is unit force per unit length, so Newton per meter. This is the answer. Thank you one and all.